Welcome to CWM's latest webinar, a comprehensive overview of die-cast dies. I see that people are still coming in, so I'll wait a couple more minutes to allow people to log into the system and get situated before we start. Again, I would like to welcome everyone to the webinar, a comprehensive overview of die-cast dies. This webinar was created as an in-depth introduction to die-cast dies and their functionality and purpose. My name is Roseanne Rimical. I'm the marketing coordinator here at Chicago White Metal, and before we get into the topic, I do want to go over a few of the general details about our webinar so that you can take advantage of all the options that you have on this presentation. I just want you to know that your questions are welcome, and we ask that you please use the questions feature to send your questions to our live Q&A panelists. And feel free to email us at sales@cwmtl.com directly, or give us a call, 630-595-4424, with any additional questions, or if you are interested to discuss a potential or existing project with us. Our live Q&A panelists will be available throughout the webinar and for about 5 to 10 minutes after the presentation is over to answer any questions you may have. Our die casting specialists are John Miller, Vice President of Sales and Marketing, Mike Dimitrov, Inside Sales Manager, and Jody Scollard, our Business Development Manager here at CWM. Now I would like to introduce you to our presenter, Rob Malarkey. He's the Director of Engineering at Chicago White Metal, and he's been with CWM for about 7 years, extensive experience as an engineering project manager, and he also serves on the board of Chapter 5 of the North American Die Casting Association. So without further ado, I am turning this presentation over to Rob.
My name is Rob Malarkey. I'm the Director of Engineering here at Chicago White Metal. Been here for 7 years, and prior to this role, I was also a engineering project manager here. So I'm very familiar with the tooling aspects that we'll be discussing today. So I hope you enjoy. So here's the webinar agenda for today. We'll start with a general description of the die-cast tool, differences between hot and cold chamber die casting, and then get into some of the individual components that go into the die-cast tool to give you a better feel for why we build our tools the way we do. And then finally, we're going to wrap up with a short video showing some of the steps that go into the die construction process. So what is a die-cast die? As you can read from the bullet points here, it's a custom engineered multi-part piece of equipment that's made from high-quality heat-treated steel. Die is composed of 2 halves. Cover half is stationary. We'll get more into that in a little bit. And the ejector half is the moving part. As the 2 halves meet, molten metal is injected into the die, held under pressure until it solidifies. And then after solidification, the metal is ejected, creating a nearly net shaped part within seconds. And then we'll get into hot chamber versus cold chamber die casting, and that describes the method that the metal is injected into the die when the tools clamp together. So we'll get into that in more detail in the next 2 slides. So hot chamber die casting is used for our magnesium and zinc alloys here at Chicago White Metal. The pot containing the molten magnesium, that's what you see here, also contains the gooseneck, which is this shape here, kind of because it looks like a gooseneck, sitting in the metal bath. You can see the gooseneck shape in the diagram above with the nozzle tip touching the die. That's right here. And the plunger comes down from the top of the machine at high speed and presses metal through the gooseneck and nozzle and into the die. Then the plunger returns, the die opens and ejects casting, and the cycle repeats. So you're seeing the injection process here. Die opens, part ejects, spray is happening right there to cool the die, lubricate it, and then rinse and repeat. So this is an example of cold chamber die casting, which is what we use in our aluminum process. Molten metal is contained in a separate furnace and then hydraulically ladled from the furnace into the horizontal shot sleeve. The plunger then travels forward, right to left in this view. So you're seeing the pouring action right now. That's the cold chamber sleeve right there. Metal pours in, and the plunger moves forward. Because the shot system is not submerged in molten metal, that's why we call it cold chamber. So on the previous slide, we saw that this system right here was actually submerged in the molten metal bath. Now we're actually outside of it. That's why it's called a cold chamber. Different types of die-cast dies can be produced here. Single cavity refers to one complete part per shot. Multi-cavity has two or more complete parts per shot. And a family die creates one or more of multiple different parts of an assembly per shot. So our CWM sales team can help you make the decision regarding which style of tool is right for you. Now we'll get into an overview of the die-cast tool itself. As we mentioned at the beginning, there's two halves that create the die-cast tool. The cover half creates one side of the part, and the ejector half creates the other half and contains the ejection system to release the part from the die. There's various names you'll see die casters refer to each half of the tool described above. As I mentioned, the cover half remains stationary on the die cast machine, and the ejector half moves back and forth to meet the cover half, and then pushes the part off the mold with ejector pins. That's why we typically design the ejector half of the part as the side most likely to stick to steel. If your shot sticks to the cover half, there aren't any pins to push the part off. We won't spend too much time on these overview slides. This is just to give you an idea of how the whole die is assembled and works together. So this is the front of the cover or stationary half, and the back of the cover stationary half. The ejector half is a bit more complicated on the front than the ejector half did. Not so bad on the back of the ejector half, but let's get rid of the back plate and see what's underneath that. And it's a bit more complicated. So this is showing the back of the ejection system that moves forward with the ejector pins to push the part off the mold. The rest of the components you see on here support the die against the back plate for even pressure distribution on the platen. Or they could have cooling components, so we'll get more into these bubblers a little bit later. Okay, moving on to the individual components associated with the die. So the mold base is responsible for containing the cavities and providing enough material around the cavities to contain all the molten metal under pressure. The mold base is softer than cavity steel to allow for slight deformations under clamping pressure, and as it says here, the mold base does not usually contain water or oil lines, but it can in some cases. Most of the holes you see here are clearance holes to allow pipes access directly to the cavities, and this allows water and oil fittings to be outside the die where the caster can access them if necessary. The last bullet point describes a CWM specific standard due to the design of our cold chamber shot well system. This isn't something a customer needs to be concerned about on a new die, but it would come into play on transfer tools. Probably the most important piece of the die-cast tool, the cavity block creates the final geometry of the part. They're made from premium H13 steel, hardened to 46 to 48 Rockwell. Contain cooling lines, oil lines, thermocouples, core pins, ejector pins. Because molten die-cast metal shrinks as the metal cools and freezes to solid, the cavities are built 1.006 inches larger per inch in all directions, so that when the final solidified casting comes out, it conforms to the print. Shot block contains the shot well sleeve where metal comes in from the shot end of the machine. Contains cooling lines just like the cavity steel and is made from the same material. Rails are the main support components in the ejector half of the tool. They support the ejector mold base against the back plate or the ejector platen of the machine while providing space for the ejector plates to move back and forth. The oval holes you see here allow the operator to see into the ejection system if necessary and to add grease to keep things moving smoothly. The back plate, which touches the rail or is in between the rails and the platen, distributes the clamping force to the machine ejector platen. Otherwise, you risk clamping with high pressure to just the support pillars and the rails, and this can cause what we call coining of the machine platen and will cause the platen to be out of flat. You'll actually get divots where you're pressing and clamping under high pressure. It's an optional component for some die casters, but we feel it's necessary to keep our dies and platens in good shape. All right, leader pins and bushings. We design our leader pins on the ejector half and our leader pin bushings on the cover half. All they're meant to do is, as the die closes, the leader pins guide the die into alignment for a perfect fit before the tool fully clamps. And this is just an example of a vent at the back of the cover half where the bushing comes in to allow air and debris to escape if necessary. Eyebolt holes, we add eyebolt holes onto every component over 25 pounds for the safety and ergonomics of the tool room and the production employees. Clamping slots, this is what we use, just like the name implies, to clamp each half of the tool onto the platen surface. The dimensions you see above here are standard for CWM, but they'll vary by die caster. Again, not something you need to worry about up front for a new tool, but something to keep under consideration for a transfer tool situation. Safety strap. So when you're setting up a die cast tool in one piece, it would be a bad thing generally if one half slipped off the other before you had the tool fully clamped. So the safety strap prevents that from happening during the setup. When you're ready to open the tool after each half is fully clamped, you simply remove one bolt in the safety strap to release it. These screws have clearance holes through the back of the mold base and thread into the cavity, typically in 4 locations. They hold the cavity tightly into the cavity pockets in the mold base. These holes or the knockout holes can be used to remove the cavities for service or preventive maintenance. Return pins, we'll get into these a bit more when we discuss the ejection system in greater detail, but their main responsibility is to contact the cover half mold base at the front end during clamping to make sure the ejector system, including all the ejector pins, are fully returned to their starting position before making the next shot. Core pins are used to cast holes in parts. These holes could be directly tapped after machining or simply used as metal savers to reduce weight. Due to the fragile shape of the core pin, they are made replaceable to allow for a quick fix compared to welding and remachining the feature. Body diameters are standard fractional inches for easier manufacturability. Ejector pins are similar to core pins. These are easily replaced components that basically push the part off the ejector half. If the end of the pin is contoured to the part, the pin head can be keyed and clocked in the appropriate direction to prevent rotation and to hold the geometry of the end part over time. Vent or chill blocks are a useful, sometimes optional component on CWM tools. They allow for a more compact venting system and allow more air to escape from the cavity when a large side action prevents the necessary amount of traditional venting. This makes them excellent choices for high volume or high complexity or highly cosmetic castings. And we can help you decide when this optional component is going to be necessary. Okay, the next set of slides can be a bit confusing for somebody not familiar with cam-driven ejection systems, but we'll do our best to simplify here. In most die-cast tools designs, all the ejector pins are sandwiched between 2 plates, what we call a 2-plate system. As the system moves back and forth, all the pins move the same amount back and forth. Usually the part is ejected and a robot grabs the part to extract in these systems. What we do at CWM is we use a cam-driven 4-plate system separated into basically two 2-plate systems. The back 2 plates, which we'll refer to as 3 and 4, contain most of the ejector pins. So as the whole system moves forward for ejection, plates 1 and 2 are activated with the cam system and drive 3 ejector pins a bit further forward than the rest of the pins. So what this does is it kicks the shot off the rest of the pins and down into a quench pit in the floor. So because CWM doesn't need to wait for a robot to extract the parts, we're able to achieve a faster cycle time and a lower price for the end customer. So this is a brief written description of what we just discussed, but we'll move on to the picture explanation. It's a little bit easier to understand. Okay, so this is position 1. We'll call this full back. The plates are in this position when the die is clamped and when the die is open just after making the shot, when you have the solidified part, and before any of the ejection system begins to move forward. So at this point, you've got a complete shot in the die. It's not shown here, and you're ready to start the ejection process. So the next step is the plates move forward. We'll call this contact because of the contact that you see at the end of these kicker pins right here and right here. They're actually touching the mold base. So the kicker pins contact the back of the ejector mold base. At this point, the complete shot is released from the tool, but it's still hanging on all of those ejector pins. So this next position is what we call the cam activation. The ejection system moves just a bit further forward from position 2. So plates 3 and 4, these back two here and these two right here, move that same small amount forward, but due to the cam rocking forward and pushing plates 1 and 2 even further forward, the kicker pins activate and the casting falls off the rest of the pins. So the casting is now in the quench pit and we're ready to return the ejection system to position 1. A little bit before we get there, we end up in the pullback activated position. So at this point, you can see the plates return and that we've almost gotten back to position 1, but plates 1 and 2 are still separated. But you remember those return pins that we discussed earlier and we said we would mention it a little bit later? Well, now they come into play. They aren't shown here, but as the die closes, they contact the other half of the tool and push that little gap together between plates 1 and 2 and 3 and 4. So then we end up back at position 1 before we start the next cycle and we're ready to make a shot. So 2 types of hydraulic pullback systems. The plates work the same in either case, but the actual component that's associated with the machine that's pushing the plates back and forth is a little bit different. So aluminum uses a central hydraulic pullback in general, and magnesium uses pullback rods in general. So we'll get into that in a little bit here. Central pullback system. So here's an example of what the central pullback system looks like. We won't go into all the details here, but this is what it looks like when it's installed in an aluminum machine. And here's a cross-sectional view. The adapter disc that you see right here is actually attached to the machine and moves the system back and forth. When the die is set up, the horseshoe bracket, which is this piece right here, actually gets inserted from the top and then locks into this in between the cage and the ejection system in the die, and that's what holds everything together, allowing it to move back and forth. So then when you're ready to remove the die, you just remove this fork from the top again and you're ready to tear down the setup. Pullback rods are a little bit different, but in general accomplish the same thing. Rather than attaching the machine to the die with that horseshoe bracket that we mentioned in the previous slide, the pullback rods directly thread into the ejector plates and the machine, joining them together. All right, we'll get into the cooling and thermal system components at this point. So we'll start with thermocouples. These thermocouples are inserted into each half of the tool, sometimes into multiple areas. This helps CWM monitor internal temperatures of steel and regulate our process water. So a hotter than normal reading on a thermocouple indicates the steel is too hot. So water lines nearby increase in flow cool that area down automatically. Similarly, if we found that the thermocouple was reading too low, we would decrease the flow of water in that area, and then the die would begin to heat up as you make shots over time. These components are called bubblers, or sometimes cascades. You'll see both names used interchangeably. So standard cooling and oil lines flow in a straight path from one side of the cavity to the other, cooling or heating everything the water oil touches the surface of the cavity steel. But what happens if you have a tall piece of steel that you can't access with a normal cooling line? That's where bubblers or baffles that we'll show in the next slide come into play. The bubbler shown here is a thin-walled hollow tube that is inserted into the cavity. Water flows through the inside of the tube. That you'll see it'll come in from here through the tube shown in blue. It'll exit at the tip and cool the tip most effectively. That's where you'll get the highest cooling effectivity. And it'll actually flow down around the outside of this tube and then back out here. So the different examples that you see here are all the same component. They're just installed in slightly different areas on the die. Similar in use to a bubbler, a baffle works by getting water or oil into tall, somewhat inaccessible areas of the die, but it works a little bit differently in that you're actually splitting a conventional line that can't go up into this area, traveling up one side of the blade and then back down and then out. Similarly, it will travel up this one, back down, and then out. Usually they're straight blades. You can see what we call turbo baffles, which are these twisted baffles. So it'll travel, hit here, and then spiral up one side, and then spiral back down the other side and back out the die. Sometimes the geometry of each part is a little more complex than just open and shut. Picture casting a tube. Each half of the tool creates one half of the OD of the tube, but what creates the ID? So in order for the die to open and for the part to eject, you need to be able to move steel into the cavity to create the ID, and then move it out of the way before ejection. So that's what we call a side action. Simplest type of side action is mechanical. Springs on top of the side action are strong enough to hold the slide up and out of the way when the die is open, allowing the part to eject. And then when the die closes, the angle pin shown on the right here, guides the slide into place and down into the molding area of the shot as the die clamps. And then we make the shot. And then when you're ready to open the die, the springs are now in compression and extend against the slide stop, and they pull that slide out of the way for ejection. So that's how it works from shot to shot. So you can see here, this is a view through that side action that we were just looking at and a section cut. So here it is just before clamping. And in the section cut, you can see that the angle pin is about to align with this angle pin hole in the slide. And then here we are fully clamped, and if you section cut through and we're able to see into it, this angle pin is now fully into the slide carrier. And as it's moved from left to right, it's moved this side action down along that angle pin. So now it's in place and ready to make the part geometry. So the slide tip is what we call the molding portion of the side action. Very similar in application to the cavity steel, made with premium H13, just like the cavities, and hardened to the same spec. And it can contain cooling lines just like cavity steel as well. The slide spring and bolts, as we mentioned in the previous slide, the springs help return the side action when the die opens and keep the side action in place during ejection and clamping. Gibs, these are optional components that go on either side of the side action to hold it in place and give the side action a rail to slide against. As the die ages, or in the case of damage occurring, these gibs can be removed in the case the slide is seized in place due to leaking metal into the slide pocket or some other reason that doesn't allow the slide to move. This is an advantage over machining these directly into the mold base. If the slide seizes in place without gibs, you really have to use brute force to kind of get that seized side action out of the mold base. And then at that point, once it's out, you have to determine, do you need to make repairs to the slide carrier or to the mold base itself, or maybe both. Slide stop is pretty self-explanatory. It's the piece that is in between the side action and the springs, and then when the die is open, the slide springs pull up against the slide stop, and the slide actually stops on the underside of this piece. Just like the slide tip was similar to the cavity, the slide carrier is very similar to the mold base. It's made of softer steel, just like the mold base, and it guides the slide into place and holds it in place against the slide lock. It's also got clearance holes for bolts and water pipes, just like the mold base. The slide lock is made from hardened steel, like the Gibbs, and the slide lock is on the opposite side of the tool from the side action and slides along the carrier and holds the slide in place when the shot is made. This is what keeps your side action from blowing apart as you're making the shot. Angle pin, the name comes from the fact that it's a pin on an angle. It guides the slide carrier into position before the shot's made and guides the carrier out when the tool opens for ejection. Now we'll move on to something a little bit, I guess we'll call it a little more complicated than a mechanical side action. This is a hydraulic side action. So hydraulic slides can be used instead of mechanical slides, and we might elect to use hydraulic slide instead of mechanical slide if the slide needs to travel a relatively far distance, or the side action is relatively large, or if there are geometry constraints or other special circumstances where a mechanical slide won't work. Hydraulic slide may be more expensive than mechanical slide, but sometimes it's a necessity. Here's just a rough picture of a hydraulic cylinder. So it's responsible for moving the slide back and forth. Pressurizing one port moves the slide in, and pressurizing the other moves the slide out. This is the example of a hydraulic cylinder bracket. Really simply there to attach the hydraulic cylinder to the mold base. The large hole that you see in the center is a clearance hole for the plunger and the adapter that's actually going to connect to the side action. The hydraulic cylinder adapter, so this is the shaft of the hydraulic cylinder, so this is just a section view, so normally you'd see the cylinder itself here, and then this adapter threads onto that shaft, and then this feature right here is actually what slips into the slide carrier, connecting the whole system together. Limit switches, very useful for sending signals from the die to the die cast machine so they can communicate. When everything on the die is working as it should, these aren't necessary, but not everything always works as it should. So if a component seizes or breaks or wears and the component isn't where it should be, this limit switch is sending a signal to the machine telling you not to close and that something is wrong, so you can prevent some pretty serious damage to the die. You'll find these most often on the ejector system and hydraulic slides. Those limit switches need to be in very precise locations, so we create these little brackets that attach underneath them that allow for some slight adjustments in the X and Y position. This is a limit switch actuator. So this is a piece that is solely used to connect the position of the slide or the side action and translate that to a position on the limit switch. So as the hydraulic cylinder moves back and forth, so does the limit switch actuator. And these little round pieces that you see here that are adjustable on the rod actually contact that limit switch and let the machine know that the slide is or isn't in place. So everything we've talked about at this point is really applicable to either cold chamber or hot chamber dies. But hot chamber specifically has a couple special components that it's worth mentioning in this. So here's a view of the cover half, the front and the back. So one of the things that is different is this bushing here. This is the front of it. Here's the back of it. The nozzle locator ring and the magnesium locators. So we'll get into those in a bit. Here's the ejector half. Just like you saw, the bushing was a special component on the cover half. The spreader that you see here is a special component on the ejector half. And then on the back, we've already mentioned these are the hydraulic pullback rod locations that we use for magnesium. The spreader and bushing. These components guide metal from the nozzle into the runner system of a magnesium or a zinc tool. Zinc runs at relatively low temperatures and is not as volatile with water, so a swage two-piece spreader and bushing can be used. Molten magnesium, however, is very reactive with water in a bad way, so custom hardened single-piece bushings and spreaders made from H13 are going to be required. These are the hottest components of a hot chamber die, so they need to be built to last. Nozzle locator ring, as the name implies, basically it's there to align the nozzle to the bushing for a perfect fit, and that allows no metal to leak from the nozzle or the bushing while the shot's being made under high pressure. Magnesium locator, unlike cold chamber dies, the cold chamber die has a shot well that sticks out of the platen and then is installed into the die, so that automatically aligns your die to the cover half platen, and then you can clamp both halves together. Magnesium doesn't allow for that contact on the nozzle to be used as a location position. So we have to actually install these locators on all of our magnesium tools, and they'll fit into slots, the same clamping slots that are already in the platen. So this is how we align any hot chamber tool, whether it's magnesium or zinc. And now we'll get into a short video showing the tool making process. It's really brief, and these aren't necessarily our tool makers, but the general concept and steps taken to develop a tool are presented here.
Okay, so the first step we go through is going through the mold flow analysis, which is what you see here. That helps us design the shot and then the die around that shot, as you see here. Once we're ready to start cutting chips, we'll go through a rough machine of the mold base and any components, and then go through the heat treating process. So typically for the premium H13 that we use a vacuum heat treat process. So they'll drop the pressure in the system pretty near vacuum, and then they'll inject it with usually nitrogen or something like that, something that's going to be non-reactive with the steel. And then go through the heat treat process. So that'll mean heating it up to a certain temperature and then cooling it down to a certain temperature over a period of time, and then reheating, cooling it down, and it'll go through a couple different cycles. And that's the heat treatment process that we need to do to bring this steel to the right hardness and other material properties that we need. So then after it's hardened, we do the finish machining, so you're not taking off anywhere near as much as you were in the rough machining, just those last few thousandths of an inch. Go through polishing, and then the fit and assembly of the die. Even if things are, machined to within 1 or 2 or 5 thou of where they're supposed to be theoretically, it always takes a little bit of handwork and nuance to get things to fit together. They'll apply a blue dye to each of the moving components and then close everything together and then check where that dye transfers to the other components. So what you see here is an example of them putting everything together and doing the first initial fit. So they're closing it slowly to make sure that if something isn't going to work, that they don't cause damage. And then afterwards they'll check that dye to see if it transferred properly. And then each one of our dyes is going to go through a sampling process, whether it's made here or whether it's made internationally.
Thank you so much, Rob, for presenting the topic of die-cast dies to us. And also thank you to all of our attendees for taking the time out with the presentation of the die-cast dies. And just want to go over a few more details, some of the reference materials that we used. I will make these available to all webinar participants and attendees. Here are a few of the reference materials that we have available to our webinar attendees for the downloadable items. Each of you will receive an email from me, and the links will prompt you to either log into an existing account in our Die-Cast Design Center or to create a new account, which is free to do. So once you create the new account and the account has been approved, you will have access to an entire library of resources that we have available to anybody who would like to subscribe. And again, this is at no cost to you, so definitely take advantage so that you can have the resources available to you to make that die-cast design decision. And I also wanted to reiterate that we do have some people to contact should you have any additional questions regarding specific projects that you're working on. So here's a list of initial points of contacts to discuss those projects, new or existing. And I included my information as well, just in case you have a question on the website or Die-Cast Design Center or other marketing related items. So our team has many years of experience in die casting, so they should be able to assist you with any questions that you may have. Thank you again for attending our webinar. We do appreciate your attendance, and also we'll keep our live Q&A open for about 5 to 10 minutes to answer any questions that you may have. So with that, I hope you all have a great day, and I am signing off. Thank you.